Hello, everybody. Thank you for taking the time to join us and watch this webinar. I think we have a pretty interesting topic to discuss. We've got in ProMax 6.0 a lot of new features, and one of these is this pair of electrolysis blocks, which will allow us to simulate the production of hydrogen and oxygen from water and electricity. So we've been working on this for a couple of years now, and we finally got it. We originally were simulating these electrolysis and fuel cell models using our basic blocks with a lot of calculators, specifiers, solvers, user values, and we were doing that. But we even added it into our BRE 141 Sustainable Hydrogen Technologies class, and it's nice to have the ability to do that. But it was obvious that it was a little too cumbersome and difficult to change specifications. So we decided to add a real ProMax process block into ProMax so that it's very easy now to model electrolysis. And hopefully it becomes very popular. And if so, I think we would then decide to add the fuel cell. But right now, the electrolysis is by far the more popular topic and the one that is needed at the moment. My name is Barry Burr, and I've been at BRE for 17 years now, I guess, and I've done several roles, covered territories as a consulting engineer. I've been a refinery specialist, and for the last couple of years, I've spent a lot of my time on electrolysis and fuel cells and trying to develop our capabilities so we could have this block. So uh, after the presentation, we're going to have several models, projects, ProMax projects that will be presented. And if you'd like to have those, then please write my email down right now and just contact me later. I'll be glad to send the ProMax model files to you. And we will have a video of this presentation posted on YouTube or on our website at some point in the future. I can't say when that'll happen, but this presentation will be on YouTube so that it could be viewed by you later or by other people that you know. So feel free to forward it if you think it's worthwhile. So today what we're going to talk about, first we're going to talk about the types of electrolyzers that we've added to 6.0. We have two process blocks because some have two feed streams and some have one feed stream, but that's really the only difference. And then I'm going to go into a little bit of theory, a little bit of background on electrolysis, electrochemistry, but not very much because I have not yet mastered the technique for presenting a lot of electrochemistry in a short amount of time without losing people. So I'm going to try to keep the theoretical part very short and sweet and just kind of notify you of the key concepts that I think are important, and hopefully you can learn more of those later on if you want to. And then we're going to go into the really good part of the presentation, I think, which is to show how to simulate alkaline water, PEM, and high temperature electrolysis. And when doing so, we'll kind of introduce you to the key features of the blocks so that you know what all the parameters mean and what you're able to do with the blocks. And those simulations will be just the the feed streams to the electrolyzers and their immediate product streams. And then I'll show you a built simulation of a couple of alkaline water electrolyzers with the balance of plant equipment, or the balance of plant simulated around them. So that's what we're going to talk about today. And so as we move into it, you can see here are the two electrolyzer blocks that we've added to ProMax. To find them, you want to go into ProMax's auxiliary objects right here. So we've always had this stencil It's where our divider, pipeline, makeup, blowdown, you're familiar with those blocks. But at the bottom, we've now added these two electrolysis blocks. So this one here with a single feed stream is what you'll use if you want to model PEM electrolysis. And it's kind of funny, but PEM seems to equally stand for polymer electrolyte membrane electrolysis or proton exchange membrane electrolysis. I see it just about equally represented when I try to, research on this topic. But, I don't know how that happened, but it's kind of funny that the acronym has two different popular ways of describing it. And then we have, for our dual feed, we have alkaline water and high temperature electrolysis, which are to be used in this dual feed electrolyzer block. And high temperature electrolysis, at least these days, has been entirely represented by solid oxide electrolysis. So there may be other electrochemistry type of cells that operate at high temperature, and there are some unique aspects of operating at high temperature, but so far it's always been solid oxide electrolyzers that I've encountered that require the high temperature option. So to go into a little bit of background on electrolysis, the first thing that I would like you to know is that I don't want to spend a lot of time on theory in this presentation. So if you want to learn more, the place where I started learning about electrolysis the best and the fastest was on the PEM electrolysis Wikipedia site. They do a very good job of explaining the key concepts, and I recommend that you go there if you want to learn more about the topic. And when you go in there, you'll see that the different electrolytic processes that convert water into hydrogen and oxygen, they involve different types of half reactions. So all the electrolyzers have different sets of half reactions, but the good thing is that they all end up having the same overall reaction. So it doesn't matter whether you're using PEM or alkaline water or solid oxide, they all have the same water that is being converted into a mole of hydrogen and a half mole of oxygen. And along with this, there are 2 moles of electrons per mole of water that are required for this overall reaction. So the key idea that one of the key ideas that we need to appreciate in electrolysis is this concept of a thermal neutral voltage. So at constant temperature and pressure, and then at 25 C and atmospheric pressure is where you would get the standard thermoneutral voltage. But at any temperature and pressure, so long as you conduct the reaction at constant temperature and pressure, the energy required to carry on that reaction, the heat of reaction, is something that we as chemical engineers, most of the audience here are chemical engineers, will think in terms of the heat of the reaction or the change in enthalpy of the reaction. But when you look in the references that describe these different electrolytical processes, they'll usually characterize them in terms of a ideal or thermoneutral voltage. And for the electrolysis of water at standard conditions, that voltage is 1.48 volts. So here we have a voltage, but it corresponds to a heat of reaction. So in, we have a chemical engineering side of this, which is the reaction of water into hydrogen and oxygen and the energy required to carry that out. But there's also all of this electrical engineering terminology that's floating around, such as voltage, and we'll talk about power in watts, and we'll talk about current in amperes, or current density, which is how much current is flowing through a membrane per unit area. So these electrical engineering terms are going to also be discussed in the topic of electrolysis. So we need a way of relating the chemical engineering and the electrical engineering to each other. So, after 30 years of being a practicing chemical engineer, I finally, for the first time, ran into Faraday's constant. So this last 2 years, I've been dealing with Faraday's constant a lot. And here you can see that Faraday's constant is 96,486 coulombs per mole. And a coulomb is a unit of charge that's equivalent to 1 amp that's happening for 1 second. So that's how much charge is there if you have 1 amp of current flowing for 1 second. And then there's this key equation that I think is the real bridge between the electrical side and the chemical side for electrolysis. And this thermal neutral voltage is equal to the heat of reaction in a energy per time unit, like joules per second, divided by 2, representing the stoichiometry of the electrons to water, and the Faraday's constant and the molar flow rate of the water. So that's how you can relate the, in the chemical engineering, we have the heat of reaction and molar flow. And then on the electrical engineering side is this voltage, and they're related in this manner. Likewise, current can be expressed as 2 times the Faraday's constant times the molar flow of water as well. So here's how you have voltage and current, and you can see how they're related to the more chemical engineering terms that most of us are used to. So the thermal neutral voltage is something that ProMax, with its thermodynamic calculations, we do flashes, and one of the things that we can compute is the enthalpy for any mixture at any temperature and pressure. So with the ability to calculate enthalpies of streams, we can calculate the heat of reaction in ProMax. So this thermal neutral voltage is something that is best to let the simulator calculate for you. So as temperature and pressure change, the simulator can take care of getting you the right thermal neutral voltage. So this is kind of the ideal portion of it, is something that the simulator is very good at calculating. Now, if we go to the next page, there's another important energy contribution that's required, which is there's this extra voltage that is needed in any electrolyzer that's required to supply extra energy to overcome resistances in the electrolyzer apparatus, in particular the membrane. So there are various resistances. They're called activation, ohmic, and mass transfer resistances, and they kind of caused by friction of these molecules as they're moving through the equipment. So this over potential voltage is something that we have to calculate and supply to get our complete electrolysis calculations. And one of the specifications that we'll ask you to make when you're using the electrolysis block is we'll ask you to enter a current density and a over potential voltage. So ProMax will take care of this orange horizontal line, which is the thermal neutral voltage, but we need you to find out what is the over potential voltage associated with this particular electrolyzer. It's an equipment specific empirical value. It's not something that can realistically be predicted by a simulator. It's something that's best. It's kind of like compressor horsepower curves, it's kind of like other equipment we have where there's a theoretical portion that the simulator can calculate, and then there's this mechanical inefficiency portion that we can't calculate. We ask you to supply that kind of information. So current density is a concept that is communicated a lot in the electrolyzer world, and that is the amount of the amperage that is flowing through a unit area of a membrane. So the current density is something to appreciate, and then the total voltage and the over potential voltage associated with that particular piece of equipment as current density changes. That's another thing to be aware of as you're trying to get enough information to simulate your electrolyzer. So just be aware that these two, the theoretical, that part that can be calculated by ProMax is there, and then there's also this calibrated or physical, experimentally measured portion that you have to consider as well. So that's all the theory or background that I want to go into. So now let's go into the fun part, which is to actually configure some electrolyzers. So I've already got the callouts that we'll need for discussing any of the results, and I've got the streams built, but they're not configured yet. And there's a place right in the middle here where we're going to add our electrolysis block. And in this case, we're going to do an alkaline water electrolysis model. It's got two feed streams going into it, so we'll use the dual inlet electrolysis block. And in this particular problem, we're given the area of the cell and the number of cells in a stack. So that's two of the three physical dimensions of an electrolyzer. The third, or a facility, and the third would be how many stacks are there in our facility. So that's one of the things that we'll calculate. And we're also going to be given the circulation rate of our KOH and water solution. And we're also going to be given the percent of the water that is converted in each pass of this reactor. And things that we can calculate then are the number of stacks of the facility, how much power is required to drive this electrolyzer, what's the temperature rise, is the extra electricity that's associated with the over potential voltage. Well, that's not gonna produce hydrogen. That's just going to be released as heat into the flowing stream. So there's going to be a temperature rise associated with that over potential power that comes from the over potential voltage. And we're going to calculate how much hydrogen is produced. So let's just walk through this simulation, and as we see the parameters of the block, I'll kind of give a brief mention of what they mean. First thing, when we're doing alkaline water electrolysis, we need to make sure that we're using an electrolytic property package. So in this case, I'll show our active environment is the caustic treating with Ping Robinson package. So this is very similar to the amine sweetening model, and the only difference is that there's a different viscosity correlation used to calculate the viscosity of caustic solutions than what we would use in the amine sweetening. But all the other electrolytic features of the amine sweetening model exist in this caustic treating model. And then for our component list, we have water and KOH, so they comprise the circulating solution that's going through the electrolyzer, and the water is the feed component. And then we have oxygen and hydrogen. They're the products of the electrolysis reaction. So those are the only components that we need. So let's specify this inlet stream. It's going to be a 30 weight percent KOH solution at 70 C, 30 bar, and 20 cubic meters per hour. Use mass fraction, 30% KOH, 70% water. Okay, should have a green stream there. And then we want to split the flow 50-50. We want half the flow going to the hydrogen side, half to the oxygen side. And now we need to find our electrolysis block. It's this one with the two inlets. Just plop it right down there. And now we can go into the electrolysis block. Now, one thing I want you to see is all of the feeds will go into the bottom ports of the electrolysis block. And if you zoom in, if we zoom in, you'll see that the right hand side has got a little H2, meaning this is the hydrogen side of the block. And then there's a little O2, meaning this is the oxygen side. There is a port that's got this little blue blue with a lightning bolt through it shape, or a kind of icon, and that is where you want to connect your electrical power energy stream. And then there's the option of adding or withdrawing some heat. So there's a place for a thermal energy stream to enter or be withdrawn from. And we'll use that when we go to the solid oxide case. So now let's go back to where we can see this better. Now, if we open the block with the project viewer, you see the connection stream. We see our standard connections here. There is a optional stream for the thermal energy. At the very top in the configuration, we have a selector where we can choose here we can choose alkaline water or high temperature electrolysis so we can choose which type of electrolyzer we're running. And then we're going to have these properties, which I'll briefly describe as we go through the construction of this electrolyzer. First, there's pressure drop. So the feed can have a pressure drop. In some cases, it can have a pressure rise to the product side. And in this case, we just want to have no pressure drop. There's going to be no pressure drop from the oxygen side inlet to the oxygen side outlet. Same with the hydrogen side. And one property we have it's not a property that you would at the end of your simulation work you would want to use for specifying your electrolyzer, but at the beginning of your process of specifying your electrolyzer, I really recommend that you use this water conversion property. If you know the typical amount of water converted in a particular type of electrolyzer, then you can use this, and regardless of how incorrectly you have guessed your circulating feed stream, you'll always get a decent result. So the problem that I'm trying to avoid is if you guess incorrectly on the circulating feed stream and then you set the power to be the power that you want it to run at. If you guess wrong, you might have not enough flowing feed, and it might be so much power injected into here that you vaporize your feed and you get some kind of ridiculous results. I'd like to avoid that. So the way I recommend handling that is by initially getting your circulation nearly correct by using this water conversion, percent water converted. So here we're going to say that 3% of the feed water is converted to hydrogen and oxygen in this block. If it recycles around, it's going to be on a per pass basis. We're just simulating the immediate inlets and outlets here, but of course there's much more that you can simulate for the entire plant. So now we have this field for the overpotential voltage and the current density. So we ask that you define those, and here we say that they're 0.4 amps per centimeter squared for the current density, and we have 0.25 volts for the overpotential voltage. And if you know the total voltage of the cell, just subtract the thermoneutral voltage from the total voltage, and that will give you the cell overpotential voltage. And we have 100 cells per stack. we have a cell area of 2 meters squared, and that particular property gets entered in the cell area field right here. I think I might make a request to let that also be entered in here where you're entering this, supplying this other information. It'd probably be more intuitive if it were made available right here where these other dimensions are. But the cell area is a very common thing to enter for these, and we want to set this to 2 meters squared for the cell area. And now everything, let's see, we need to also set the crossover hydrogen and oxygen. So, we have KOH solution entering both of these streams, and there is conversion of water into hydrogen and oxygen. So hydrogen is supposed to come out of this right side as the hydrogen product, but there's a small amount of hydrogen that kind of goes the wrong way and ends up in the oxygen product. And that's what we call crossover hydrogen. The same is possible for oxygen. It's supposed to come out this effluent here, but there's some back mixing or something that caused there to be some leakage of oxygen into the hydrogen effluent stream. So we handle this by letting you specify the crossover hydrogen and oxygen. In this case, we're going to set both of them to 0.5%. Now all of our blocks have maroon outlet streams. There are no more empty cells with white backgrounds that we could put information into. So this block is completely specified. And right now we can execute this block. And I've got some results that are called out, but we also have a results table. So in this results table, you can see the total current voltage and power on a cell and a stack and a total basis. You can see the thermoneutral voltage calculated as well. So at this temperature and pressure, no matter what you enter for your overpotential voltage, you'll always get the same thermoneutral voltage and thermoneutral power. Likewise on a cell, stack, and total basis. And the overpotential voltage, and now we have a couple of properties for how much hydrogen did we produce on the hydrogen product stream, not counting anything that was carried over on the or crossed over on the hydrogen stream. This is the hydrogen yield to the desirable product, the desirable hydrogen product side, and this is the same thing expressed in a standard vapor volumetric flow rate. And then we have some calculations that are in the configuration page. We can see the change in the temperature. You see here we're going in at 70 degrees and coming out at 77.6. And we'll have the same temperature on both outlets. And this is the temperature change property we calculate. Here is the same thing, the mass and the standard volumetric flow rate yields of hydrogen, the number of stacks. We have our process is requiring enough. Our electrolyzer that we've specified here is just big enough to handle the process requirements that we have. So we only need 0.92 stacks. So we'd probably buy one of these electrolyzers and it would do the job if that level of over design or safety factor is good enough for you. And we have some efficiency calculations as well. And I think the best one of these, the one I think most people look at, is the kilowatt hours per kilogram of hydrogen. So this electrolyzer has this particular electrical efficiency. And we also can see how many kilograms of hydrogen we produce per kilowatt hour. We have that efficiency as well. There's a couple of, we think there's some other ways of describing efficiency, but we're still waiting on getting the exact definitions for those before we put them into the next release. But if anybody has, if anybody feels confident that they know the other electrolyzer efficiency terms that we might ought to be using, please send me an email and give me your thoughts on other efficiency terms that you see other people using. There's a lot of them floating around. It's kind of hard to nail down what are the real definitions for these things. But if anybody wants to help out there, please feel free to send me an email. So that is everything we need to know about our alkaline water electrolysis block. Let's move on to the next one, the PEM electrolysis. However you prefer to to describe your PEM, but this is the PEM electrolysis. In this case, we're not going to supply a single current density and over potential voltage. We're going to take the polarization curve that we found for this particular piece of equipment. And in this case, this is the polarization curve that I have. It relates the over potential voltage to the current density that's going through the membrane. In this case, we're going to fully define the equipment. So we're going to give all the dimensions, the cell area, the number of cells per stack, the number of stacks, and we're going to supply this polarization curve information. And we're going to supply the circulation rate and the electrical power. And from that, we're going to calculate the temperature rise. We're going to calculate the water conversion percent and the hydrogen production. So let's begin simulating this. This is just going to be using Ping Robinson or SRK. So the PEM electrolysis and then the next one, the solid oxide, they work just fine in our standard equation of state property packages. So let's define our inlet stream. It will be 100% water. And we're running at 80 degrees C. We're feeding at 5 bar. And we have 200,000 kilograms per hour of water circulation that's feeding this electrolyzer. We also are supplying a fixed amount of power. This is 1.5 megawatts. It's in the ballpark of the amount of power that would be supplied by a wind turbine that you might see on the ground in the United States. You know, not offshore, but a ground-based wind turbine in the United States is going to be around 1.5 megawatts. And at this point, we're ready to add our single inlet electrolyzer. And in here, we only have one choice that we can make. These other two are grayed out. You can only make the PEM electrolysis choice. What's interesting, one of the interesting things about these is you can have the feed coming in at, say, 5 bar, but it's nice that we can use this also as a hydrogen pump. So we can have the product be considerably higher in pressure. We can make this hydrogen product stream be up to 40 bar or whatever the material, you know, whatever is structurally feasible. You can pump this up to a considerably higher pressure than the feed using the membrane. The membrane will move hydrogen from a low pressure to a high pressure region. And usually on the oxygen side, we'll have a pressure drop. So here we're going to exit at 3 bar. And next we want to use a polarizer. Instead of entering a current density and an over potential voltage, we want to actually supply the points along the current density versus over potential curve. So I've saved this information over here. I've got my going to copy this information, Control C, and then I'm just going to, so I need to select more information than I have copied, type Control V, and that'll enter all those values. And we go to configuration and we'll check this box, which tells us to use the polarization curve. And then we have 100 cells per stack, and we only have one stack, and our cell area is 5,000 centimeters squared. And we have our crossover of hydrogen is 0.5% again. We have none for the oxygen, and we have this oddly named parameter called electroosmotic drag coefficient, and it only applies to the PEM electrolyzers. So some of the, as water is fed to the oxygen side, hydrogen is produced and it goes across the membrane to the oxygen side. But as that happens, each mole of hydrogen is pulling a mole of water along with it, or some number of moles of water along with it. And what I think is a good value for this parameter is 0.7. So we'll enter that. And at this point, looks like we are ready to solve the block. And we see here that with this this flow rate and this much power applied, we're only having a 1.4 degrees C temperature rise. We're producing almost 30 kilograms per hour of hydrogen, and we're losing about 0.15 kilograms per hour of hydrogen to the oxygen side product. And you can see that temperature rise here. You see our yield of hydrogen, and you can see that at this condition, we have 0.133% water being converted, and that's a reasonable value for a PEM electrolyzer. And here you can see at this amount of power that we're supplying, this is where we are on the current density and over potential voltage graph. So because we specified all the dimensions, as we change power, we're changing current density, and the block is determining what the current density is and the over potential voltage from the values of the curve that we entered. And here's our electrical efficiency, a little bit lower than we saw on the alkaline water case. Here are our overall results. So you can see how everything lines up on a stack basis, cell basis, total facility basis. So I think that's all there is really to talk about with the PEM electrolyzer. So that we can move on to the solid oxide electrolyzer, our last type of electrolyzer. Okay, so here we have solid oxide. This is going to occur at a high temperature, 700 degrees C. It's quite hot. And one thing about being this hot is that any crossover hydrogen that gets to the oxygen side, well, it's going to combust and form water. So the hydrogen will combust with the oxygen it sees and form water. So at these high temperatures, the crossover hydrogen and oxygen just form water, and they form heat. So you won't see the crossover hydrogen and oxygen in the product streams if you analyze them, but you'll see a temperature rise that's more than you would expect for that type of for the thermoneutral voltage plus your expected over potential voltage. And another interesting thing is about these is that they tend to have negative over potential voltage. And what that means is that to run these, you actually need some supplemental heat that is coming in at a high temperature. So these processes tend to need some high temperature heat to keep them running at the desired outlet temperature. So in this case, we're going to, our inlet streams are already defined, and you see the conditions are already defined in here. And we are going to get our electrolysis block now, the 2 input, 2 feed electrolyzer block. And initially it turns pink because the default electrolysis type is alkaline water. and we have there's a message that it expects to have caustic solution here. So we have to change this to the high temperature electrolysis type, and then it goes back to being a nice blue block. And the first, we have a no pressure drop on these. And typically the water that's coming in the hydrogen side feed is where we have our water in the form of steam. And because of some recycles, we end up having this steam plus hydrogen recycle stream. And on the other side, we have air coming in. And both of these are hot, but the steam that converts, typically these are like about 50% conversion of the steam happens per pass in the solid oxide electrolyzer. And as I mentioned, we can have negative overpotential. So we're going to have at a 0.4 current density, we're actually going to have a negative 0.1 overpotential voltage. So it means that if you ran this without supplying any, like the other electrolyzers, if you ran them, they're going to have a temperature rise, and we'll have a heat exchanger somewhere in the recycles of those circulating fluids that will remove that heat. But in this case, you got something that's causing the temperature to go down, and you need to provide some supplemental heat to keep this electrolyzer from just cooling off. And we have a cell area of 1 meter squared. We have, in this case, we have 300 cells in this stack. And initially, we're going to look at the case where there's no crossover hydrogen. I think we're ready to, let's see, there's something that feels like I'm missing something. I don't think it's going to, okay, it does. It was completely configured. That was, my eyes were making me think that was red colored outlet streams there for a second. So notice here, we don't have any heat being supplied. We don't have any crossover hydrogen or oxygen causing combustion and heating. So we see that we go in at 700 degrees C and we come out at 581 degrees C. That's because of that negative 0.1 volt overpotential. So it's quite different from the other electrolyzers that we have. So now that we have that, let's look at what happens if we have some crossover hydrogen and oxygen. Let's say we're going to have 2% of the hydrogen crosses over and 2% of the oxygen crosses over. Okay. So now, instead of 581 degrees C, the heat release due to the combustion of the hydrogen heats the effluent streams from 581 up to 642 degrees C. And you also see that there is no hydrogen in the oxygen product, and there's no oxygen in the hydrogen product. Okay. So whatever crossover occurs, it combusts completely, releases heat, and leaves behind none of its crossover material in the product stream. We have a property down here that says allow Gibbs reaction on the product. So what we're doing is if there's any crossover, we feed them through Gibbs reactors on these products. So it'll be an equilibrium calculation. So it's not necessarily going to be 0%. If the Gibbs minimization says you should have, remaining 0.0001% hydrogen, you'll see that answer. But if we uncheck that, now we're not going to let the crossover hydrogen and oxygen react or combust. And we run this now, and we see we go back to that original 581 degrees C, and now we see the hydrogen that crossed over into the oxygen, and we see the oxygen that crossed over into the hydrogen. We see that information now because we didn't let it participate in the Gibbs reactions. Okay, so there's a way you can see the effect of a certain amount of hydrogen or oxygen crossover. So I'm going to put that back there to where it was before. And now what we'd really like to have is we don't want this exit temperature to be 642. What we really want is we want to add some supplemental heat to the electrolyzer so that we end up being able to set the product temperature to 720 degrees C. If we make it 700, then in the normal balance of plant flow sheets, there will be a feed effluent exchanger on each side, and you want to have a temperature difference so that you have an approach. So you want to have this a little bit hotter than your feed so that you have a positive approach temperature. So now we're setting this to 720, and you can see that we need 1.651 megawatts of electrical power to conduct this electrolysis and make this 81.6 kilograms per hour of hydrogen. And we also need 0.09. I put it in megawatts just so it could be apples to apples looking. So we have like 0.1 megawatts of heat that we need to add in order to maintain this process's temperature to desired outlet of 720 degrees C. And here is the electrical efficiency. What you can see here is that this is considerably more efficient. And this is the big advantage of the solid oxide electrolyzer, is that this is considerably more efficient than the other two processes where the efficiencies were like 46 and 50 kilowatt hours per kilogram of hydrogen. So that's the big advantage of solid oxide. It has some complexities that it runs at high temperature. It needs this high temperature supplemental heat. So, those are everything has its pros and cons, but that's the big advantage of the solid oxide. And that's a pretty significant electrical efficiency advantage. I just have the feeling that, in 20 years that this will be the winning technology because of that efficiency, that all the other associated problems people will solve, but nobody can fix thermodynamics. So I think that's what's going to make this eventually the superior technology, although it's a distant third right now in terms of market share. So anyway, those are the configurations of the three types of electrolyzers we'll commonly see. And now I just kind of wanted to give you a picture of what would be the balance, a simple balance of plant model for a alkaline water electrolysis. And there's two types, and they do make a pretty big difference. There's one type where the effluents are fed to a oxygen and hydrogen separators, and we knock out the water phase in each of them, and then we mix them back together into a single combined effluent, and then we pump them, and then we determine what our makeup flow rate of water needs to be in order to make our desired flow rate and our desired KOH composition. So this is a makeup blowdown block, just like you've seen in our amine sweetening units, except here we're trying to target 30 weight percent of KOH, and we're going to let the rest of the added volume be supplied by pure water. So this is how we bring in the water that we've lost due to the reaction of electrolysis reaction. And we can also lose some water to the, to saturate the vapor phases of these two vapor products. And then we remove heat. So this comes in at 78 degrees C. We need to remove this heat. So here you might want to size that heat exchanger. So all this equipment around here is stuff that you may be sizing, or you may be trying to make a process flow diagram for a project. All these pieces of equipment that are our standard simulation blocks, you can use to perform those tasks just like you normally would. And you have the electrolyzer block sitting in here, giving you the right products for whatever you're supplying into it. So this is one where Because we're, any hydrogen that ends up dissolved in this water gets mixed up here, and any oxygen dissolved here gets mixed up, and they're equally likely now to go back to their, maybe to the other side. So there's some hydrogen going into this circulating water feeding the oxygen side. And the only reason it's here is because it was dissolved in this water product from the hydrogen separator. So we end up with some considerable amount of impurity. Let's see what we have for the, we have 1% crossover hydrogen. In this case, we have a pretty high hydrogen content, but we also have no crossover oxygen, and we have a pretty high oxygen content in our hydrogen product. So there's a better way to do this, and we can segregate these flows. So these are things you would do, these are things you would do with a process simulator to optimize the design of one of these processes. You might see what happens if we segregate the flows and we keep the condensed water from the hydrogen separator in its own segregated circulation stream, and we keep the condensed water from the oxygen side in its own, and we have just this very small stream that connects these two, very small flow rate, uh, you know, 3 times 10 to the minus 12 kilograms per hour. These are so segregated, there's an unmeasurable flow rate that's connecting these two, and they each have their own makeup blowdown blocks to maintain their circulation rates and KOH concentrations. But they're segregated so any hydrogen dissolved in this water never gets to the oxygen side and vice versa. So you can see here now the oxygen, let's see, the oxygen was 0.58% in this common circulation case, and on the segregated case we're down to 0.007%. So we have a much purer hydrogen product in this case, and we have 1% less hydrogen here because of our not having the dissolved hydrogen being able to get into the oxygen circulation loop. So anyway, that's really all I wanted to show about all these simulations. And like I said, you can email me and I will send these models back to you. So, these are available to you, the presentation materials and the solved case like we have right here.